So now, assuming that we have this lemma, we can write down the following chain of equalities. Let's take a standard adjacency matrix of graph G and the distance matrix for graph G squared. So in the distance matrix of G squared, the ith jth entry corresponds to a distance between ith and jth vertices in G squared. And adjacency matrix of graph G, it does not have ones on the diagonal. It has one if and only if the corresponding pair of vertices is adjacent in G. So what if we now take the product of these matrices and look at the entry corresponding to a pair of vertices u and v? This entry is equal to scalar product of the row of this matrix corresponding to u and the column of this matrix corresponding to v. So this would be the sum over some w's. Here we would have the distance from u to w and the distance in the graph G squared, because we're taking the distance matrix for graph G squared, multiplied by the entry of the adjacency matrix corresponding to the pair wv. Now, as this guy is either 0 or 1, this sum essentially is summation of these distances only for vertices w who are neighbors of vertex v. So this is the sum of dg squared of u w, where w is the neighbor of v in G. And now if we look at this sum, what if we compare this sum to a sum of dg squared of uv for all w's in n of v? This guy does not depend on w, but still formally we can consider such a sum. Now we can see that if we have this case for u and v, then every entry in this sum is greater or equal than every entry of this sum. The corresponding entries have one kind of inequality between them. So in case 1, we have this type of inequality between the corresponding terms of the sum, and thus we have the same inequality between the sums themselves. Now, if they have the second case here, then we'd have a different kind of inequality, and moreover, this inequality would be strict, because we see that in the second case we have this thing, so the corresponding terms in our sums satisfy this kind of inequality, and moreover, there will exist one term at least for which we would have strict inequality. So that's why for the sums in total we have strict inequality in the opposite direction. But if we look at the numeric value of this sum, this is actually simple, because this sum is a sum of the similar terms that do not depend on the parameter of summation actually, and so the value of the sum is equal to the value of every single term in this sum. It's dg squared of uv multiplied by the number of terms, and the number of terms is just the degree of vertex v in G. So now we see that to actually distinguish between these two cases, we can just take the entry of the product of two matrices and then compare this entry to this number. And depending on the inequality that we have, we can actually reconstruct the distance between u and v in G, assuming that we know the distance between these vertices in G squared. So if we have this inequality, we have first case, and if we have this inequality, we have the other case. So now, what kind of data do we need to perform this kind of reconstruction, and how fast can we compute all the needed values? So assuming that we already have this matrix, and we definitely have this matrix, we see that to compute all the distances between all the pairs of u and v, we need to perform first the multiplication of matrices, which we can do in time big O of n to the power of omega. We also need to compare each entry to this product. This is just the product of numbers, and these guys are taken from the same matrix dg squared. So the number of comparisons is quadratic, and each comparison is done in constant time, and this guy is dominated by this guy. So in the end, the whole computation takes time big O of n to the power of omega. That is the time needed to reconstruct the distance matrix of G from the distance matrix of G squared. And thus now we can finally state the algorithm, the complete algorithm for computation of the distance matrix. So the Seidel's algorithm runs as follows. So first we compute the reachability matrix by squaring our matrix A hat G, and on the way, if we like, we can reduce all the values that are greater than 0 just to ones. So we compute this sequence of matrices such that n prime is greater or equal to n, and n prime is a power of 2. And the adjacency matrix for transitive closure of the graph, of an undirected graph, consists of zeros and ones. And really this is the same as the distance matrix, because in the transitive closure of the graph, if two vertices had a path between them, then the distance between them in transitive closure is just 1. If the vertices belong to different connected components, the corresponding entry for these pairs is 0. And so we have the distance matrix in this graph, like g to the power n prime, for free. It is guaranteed to be a 0-1 matrix. And now we get back by applying this procedure to get distance matrices of the graphs g to the power of n prime over 2, and so on, until we get back to the distance matrix of the graph G. And each backward step takes time big O of n to the power of omega, as well as each forward step, while we were computing the reachability, takes us the same time, and the number of these steps is logarithmic. So again, we see that in time big O of n to the power of omega times logarithm of n, we're able to reconstruct the distance matrix of the original graph. So this concludes the description of the Seidel's algorithm.